Next, we're going to introduce a particular system called distortionless transmission system. So the concept of the distortionless transmission system is if the output of the system can be represented by this equation, we call the system a distortionless system, where k is a constant and t sub d is also a constant represent the delay of the system. The characteristic of the distortion can be described in the time domain using this impulse response. And here's the graphic representation of the system in the time domain. Equivalently, we can also describe the same system in the frequency domain using the frequency response. The amplitude response is a constant, while the phase response is in linear relationship with the frequency. Here is one example. If we have a stable continuous time LTI system, determine whether the system is a distortion transmission system and try to find the response of signal to this signal. For the first question, we can rewrite the system's frequency response in this form. So it's clearly that the system's amplitude response is a constant, but the phase response is not in linear relationship with the frequency. So we can determine that the system is not a distortionless transmission system. But we can calculate the system's zero-state response. It is the sum of the two sine signals, but modified by the amplitude and phase response. And this is the waveform in the time domain. And graphically, we can show them. The blue one is the input signal, while the red dashed line is the zero-state response of the system. Clearly, the waveform is not the same as the input signal. So the distortionless transmission system can be described using this relationship. In the time domain, we can use this impulse response to describe that distortionless transmission system. And equivalently, in the frequency domain, we can use this frequency response to describe the same type of systems. Next, we're going to introduce some characteristics of ideal analog filters. Typically, we have 4 different ideal analog filters. So this is called low-pass filter, high-pass filter, band-pass, and band-stop filters. They all somehow related to the low-pass filter, and these are the mathematical description. For this low-pass filter, the frequency response can be represented by this function. So the amplitude response is a constant within this cutoff frequency, while the phase response is always equal to 0. But that definition can be extended to linear phase response. So if we have a amplitude response like this, and we have this type of phase response, this is also called an ideal low-pass analog filter. So the amplitude response is equal to a constant within the transmission band, while the phase response can be a linear function of the frequency. So that is also an ideal low-pass analog filter. So we can use this frequency response to represent any ideal low-pass analog filter. Then in the time domain, we can take the inverse Fourier transform to get the system's impulse response. And here is the representation in the time domain, and it's the waveform. Let's take a look at the waveform. We understand that the impulse response in the time domain actually is a sampling function. And in case the cutoff frequency, omega sub c, approaching to infinity, then the system becomes a distortionless transmission system because the waveform will approach to delta function. We notice that when t less than 0, the amplitude of the impulse response is not equal to 0, so that the system isn't causal. In other words, we are not able to implement that system in the reality. So it's not physically feasible. We also notice that when t equal to t sub d, impulse response will reach to its peak. This is the step response of the system. So if we take the integral of the impulse response, we get the step response. And graphically, we can represent it in this way. And please pay attention to the, we call this rising time. The rising time is inversely proportional to the cutoff frequency omega sub c. And when these omega sub c approaching to infinity, the rising time approaching to 0. But in the reality, a low-pass filter whose frequency response does not always look as regular as the ideal low-pass filter. So here is one typical amplitude response for a low-pass analog filter. Let's take one example. So the impulse response of the system is given here, and we ask you please sketch the amplitude response of the system and then determine the type of the filter of that system represents. What we can do is, we understand that this is a pair of Fourier transform. So the sampling function in the time domain corresponds to a rectangle signal in the frequency domain. And this is the multiplication by a cosine function. So based on the modulation theory, there's a convolution in the frequency domain. So this will be the frequency response of the system in the frequency domain. And clearly, this represents a band pass system. Thank you.